Okay, Unit 2, Day 1, football game number 1. Average rate of change and the definition of derivative. Yes, sir? Somehow I didn't give you a packet. Or did I give Sayla 2 and she wanted to double up? Okay, average rate of change. This was the bonus, yes, and I told you it was going to be the bonus, so hopefully you got it right yesterday. The average rate of change from A to B. Come in. Packet for you. The average rate of change, that's basically the algebra slope. I'm going to write it a bunch of different ways, because people sort of learn it different ways, but good old algebra slope. Rise over run. Change in y over change in x. y2 minus y1 over x2 minus x1. Like, all of those are saying exactly the same thing, using different words for them. Now, this specifically asks us for a function from A to B. So I want to do the same stuff, but I want to use function notation. So y is the f of, we'll do f of b minus f of a. So there's my change in y values. And the change in x values would be b minus a. Alright, so each of those statements is the same thing, but this is really the one we wanted to see, is this one at the end. That looks fancier with the function notation on there. Alright, I don't think we need to do 2 examples of this, so let's do the second example, since it's got trig stuff in there. Find the average rate of change, so change in y over change in x, of g of x equals sine of 3x from 0 to pi over 9. Okay, so I need g of pi over 9, and I'll need g of 0, and then I'll put those in the equation. Then I can do y2 minus y1 over x2 minus x1. So the sine of 3 times pi over 9. So let's see, that's the sine of pi over 3. And the sine of pi over 3 is, as I draw the picture to remind myself, sine's the y side. Pi over 3 means the y side is the long side. So root 3 over 2. And then g of 0, sine of 3 times 0. Sine of 0 is 0. Now I'm ready to do the average rate of change. G of pi over 9 minus g of 0 over pi over 9 minus 0. Maybe I should have wrote that first, because that's average rate of change, and then I went and found the pieces that I needed to find. Alright, that looks kind of ugly, so let's finish this off here. Root 3 over 2 times 9 over pi, if we want to do the keep it, change it, flip it thing. So 9 root 3 over 2 pi. Now, I have good news for you. Because in calculus, you're welcome. In calculus, we are not always concerned with, our focus is on calculus, not on algebra. So the good news is you are allowed to stop right there. Whoops, not right there. You got to evaluate. You can't stop there. You can stop right here, though. You can't leave the function notation. But once you plug things in, you can stop. We call it a safe stop. don't have to go any further. You are allowed to stop there, even with fractions and fractions. Basically, any answer that's mathematically correct is okay. So it saves you a little bit of algebra time sometimes, and maybe saves you from a mistake if you forgot how to keep it, change it, flip it, or you mess something up, or just saves you a few seconds. You can leave things like this. The trick is, most of the time your multiple choice answers, not most, all of the time your multiple choice answers are going to be simplified. You guys got victimized by the pep rally bell schedule. That's what happened during pep rally bell schedule, getting everybody. So, on a free response, you're certainly free to leave it in what would normally be a form that would lose you some points in a math class. But we're in calculus now. We're not concerned about the lesser maths. I shouldn't say that. They're important. But we got bigger fish to fry than worried about keep it, change it, flip it. We're doing calculus, so we're okay leaving things like this. Again, most of the time that would be a multiple choice question, and you have to finish it anyway. So, free response, feel free to leave answers without cleaning them up. That's okay. Okay, back up a little bit here. What does the average rate of change tell us about a curve? Do you know? I should draw a picture down. Another way to say that would be like the average slope. If that makes sense, the average slope. Because this is some curve. We pick 2 points. It's not really the slope of that line, but it's sort of the average slope of what's going on between those 2 points. All right, a derivative, definition of a derivative. The concept is it's the slope at one point. Which is kind of weird because slope formula has 2 points, right? You got to do y2 minus y1 over x2 minus x1. So how in the world are we going to do the slope at 1 point? Another word for it is the instantaneous rate of change. IROC rather than AROC. Average rate of change versus instantaneous rate of change. One more phrase for it that's not official but kind of helps. This is sort of the calculus slope as opposed to the algebra slope. Back up here. The average rate of change is the algebra slope. The instantaneous rate of change is the calculus slope. So we are switching big time here from algebra slope, get 2 points, use the slope formula, pretty easy. You've done that probably hundreds of times. Now we're going to figure out how to find the slope at one particular point. Let's start with a picture. And we want to find the slope at this point. That's x and f of x. And we want to find the slope right here. Which we don't know how to do because we don't have, you can't find the slope at one point yet. That's the point of calculus. But we could find the slope at some point over here. So let's come over here. Let's say that point is h away. So we're going to go h away from the point that we're really concerned about. So if we go h away from x, that means this is x plus h. And that y value would be f of x plus h. And that slope I can find. That's still an algebra slope, but that's better than nothing. There's my algebra slope. We call that a secant line, as opposed to a tangent line. Probably heard the term tangent line. A secant line just goes through 2 points. And we can find the slope of the secant line. In fact, let's do that. Let's find the algebra rate of change for that slope. Let's see, y2 minus y1, f of x plus h minus f of x, all over x2 minus x1, x plus h minus x. This is still algebra, right? Have not done any calculus yet. That's just the algebra 1 slope formula. Looks all fancy because we got all kinds of letters going on in there, but that's still just y2 minus y1 over x2 minus x1. I can clean up the bottom a little bit. Yeah. Okay, the next step we take is a calculus step. So I need to pause and make sure, are we okay with this algebra step? That the slope of that line is just y2 minus y1 over x2 minus x1. I mean, it looks fancy because we're using all these letters, but it's just algebra 1 slope. We're good with that? Okay. Well, the whole point of this slope at one point is to figure out the slope at this point, which would be like right there. That'd be a tangent line. Use your ID if you need a straight edge. That's a tangent line. I'd like to find the slope of that tangent line. So I'd like to sort of move my secant line into the tangent line. Let's see, for a better, closer secant line. Like, which variable, I got lots of letters on there, which variable could I adjust to make my secant line get closer to my tangent line? Somebody say it. What could I do with h that would push my secant line closer to my tangent line? Yeah, reduce it, make it smaller. Exactly. So for a better, closer secant line, let's make h smaller. Can you see that? The smaller we make h, then my secant line moves from, way over there. It starts backing up, approaching the tangent line. In fact, what we ought to do is make it much smaller. Like if we could get it really, really, really close to x, then my secant line would basically be my tangent line if I could shrink h like all the way down. Does that make sense? Well, if we shrink it all the way down, maybe we should just take the limit as h goes to 0. That would force my secant line to become my tangent line. So I want the limit as h goes to 0 of the algebra slope. F of x plus h minus f of x all over h. If I did that, then all of a sudden I've discovered my instantaneous rate of change. That is the instantaneous slope if I squished h all the way down to nothing. And if we have the instantaneous rate of change, that's the derivative of f at x. The symbol for that is that little one mark right there, f prime of x. That's the slope of a tangent line. Again, this isn't an official phrase, but to differentiate the two, it's sort of the calculus slope rather than the algebra slope. So the average rate of change and the instantaneous rate of change are related to each other. If you take your algebra rate of change and just shrink the delta x, shrink the h, shrink the change in x down to 0, you've got your slope at a point, which is the derivative. This is sort of the backbone of the entire first semester of calculus, is that the instantaneous rate of change is the derivative, is the slope at a point, or the slope of a tangent line. And you have to know all these terms because we will ask them different ways, even though we're all asking the same thing. I can ask for instantaneous rate of change, I could ask for the derivative, I could ask for f prime, I could ask for the slope of a tangent line. It all means the same thing. But you have to understand that all those words are the same thing. Okay. Definition of derivative. Well, the good news is we just did that. That's exactly what we just did. The definition of a derivative is given by, this one's got delta x's in it. So if we replace h with delta x, some people like that better because that sort of makes more sense. Like that's, if you think back to change in y over change in x, there's our change in x down there in the bottom. So this is still change in y over change in x, but we want the change in x to go to 0 so that our secant line becomes the tangent line. Delta y over delta x. I guess as long as the limit's in front of that, I should put limit delta x goes to 0 of the algebra slope. That's another way to say it. Take your algebra slope and you let the denominator shrink down to 0, and then you've got your derivative. I guess the trouble is, if your denominator is 0, that won't work, so we'll figure out that problem in a minute. Okay, some notation for the derivative of a function. We use different notations for the derivative of the function, kind of depending on the context of what's going on. The derivative of y with respect to x, it can be written all of these ways. Like, these are all exactly the same thing. So sometimes students get confused on notation. All the same thing. Derivative of f of x with respect to x. So if we just replace y with f of x, then it's all the same stuff. We just replaced y's with f's. So there's like 8 different ways to say the derivative. You can use y, or you can use f. You can use the apostrophe. You can have a parentheses or not have a parentheses. But all of those are exactly the same thing. Okay, example 1. Given that g of x, let's find g prime of x. Let's start with the definition of a derivative, and then we'll figure out where to go from there. Limit as, we have to choose here. So delta x people like because it feels like it makes more sense. It fits with change in y over change in x. It makes the connection between algebra slope and calculus slope. The reason people use h is because it's easier to write. Rather than 2 symbols, it's only 1 symbol. So you tell me, it doesn't matter. Do you want me to use, I've got notes going both ways here. Do you want me to use h or do you want me to use delta x? First vote was h. We'll use h. Again, delta x is a little more conceptual. H is just easier to write. We'll do h. Limit as h goes to 0. G of x plus h minus g of x all over H. So this is without the limit statement, it's the algebra slope. When you put the limit on there, that pushes the secant line into the tangent line, and that's the derivative. So again, don't lose sight of, we're doing algebra until we put the limit on there, and now we're doing calculus. So I need to find g of x plus h. Oh, Algebra 2 had a rough time with this yesterday on their test. They had to find g of x plus h, and some of them forgot what that meant. You guys wouldn't make that mistake. Alright, whatever's in parentheses goes in on the other side. So x plus h, x plus h. And now I've got kind of an algebra mess on my hands. Squaring x plus h. If you need to go off to the side, write it out, FOIL it, fine, but hopefully you can square x plus h without too much difficulty. Distribute the negative 2, then we'll distribute the 3. So all of that is g of x plus h. And I mean, it's correct, but this is a good time to remind us that sometimes calculus is easy and algebra is hard. So we did our algebra, we got g of x plus h. So we're going to plug that in right there. Okay, so g prime of x is the limit as h goes to 0. And I guess this lesson is tricky because you're trying to think about the concept of secant slope, tangent slope, algebra slope, calculus slope. So there's the concept side of things, but then there's also the algebra side of things of, well, you've got to be able to find g of x plus h. See if I can fit it all in right there. 3x squared plus 6xh plus 3h squared minus 2x minus 2h. Minus, need to subtract g of x now. That one's easy because they gave us g of x. I didn't have to do anything to that. I just made a minor mistake. Yes, I'm going to not do that yet, but yes. I need to subtract all of that. So Barrett, you're right. You can just distribute the minus sign kind of on the fly and make that plus. And then all over h. Again, we're trying to keep both things in mind here. We're trying to do the algebra technical computation side, but we also don't want to lose sight of the fact that we're still, even though this is really complicated, the concept isn't complicated. We're still just doing algebra 1 slope. We haven't even touched the limit part yet. So this is ugly, but it's still algebra 1 of y2 minus y1 over x2 minus x1. All right, let's clean up the numerator a little bit. What do you see that we could cancel out? Definitely the 3x squared. And then the negative 2x and what becomes positive 2x. So let's see, that leaves 6xh plus 3h squared minus 2h all over h. And maybe I overlooked this part, but what's our first step? We cleaned it up a little bit. What's supposed to be our first step on limits? Our first attempt? Yeah, substitute h equals 0. That's going to get me 0 over 0. So I got to keep going with the algebra here. What can I do next? Hopefully this doesn't blow your mind like it did my Algebra 2 students. We were doing all of this just without the limit statement, working on their algebra. Graham?
That would be the h from divide by h.
We can divide everybody by h. Like all of that's over h, so if we divide them all by h, we get 6x plus 3h minus 2. And now we can substitute and have it work. So 6x minus 2 is the derivative of g. Now, the good news is you're not supposed to know the shortcut yet, but our pre-calc classes get pretty far, and you guys know the shortcut, right? So look back at this original and think about what the shortcut is, right? We could have saved ourselves a whole bunch of time if you knew the shortcut. 6x minus 2. Power down comes down front, decrease the power by 1. And we would get 6x minus 2. Most of the time we're going to use the shortcut. You're probably sitting there thinking, why are we spinning our wheels with this algebra stuff? Why can't I use a shortcut? Because we can ask questions in such a way that sort of force you into this method. Or we can just flat out say, find the derivative using the definition of derivative, and that would force you into that method. Looking at the next example. Let's go through it quickly, because we need to get to the next page. If y equals 1 over x plus 1, write the limit expression. Oh, we don't even have to find it. We just want to write the limit expression. That makes it a little bit easier. For dy dx. So dy dx, that's the same thing as y prime. That's the derivative of y. Let's see, that's y of x plus h minus y of x all over h. I don't think that's what it wants me to stop with. I think it wants me to plug in x plus h. So 1 over x plus h plus 1 minus 1 over x plus 1 all over h. Oh, that's not quite right. I left off something. What I have written isn't wrong, I just haven't written everything I need to write. The key word there, limit expression. I need my limit in there. Right? Without the limit, that's an algebra 1 slope. To turn it into the calculus slope, I need the limit. Normally that's not a very good stopping point, but the instructions say write the limit expression, so that's the limit expression. I think that's a change we made to save time. We did evaluate limits like this on the test. You had to multiply through by, this would be an algebra nightmare, but you'd have to multiply through by x plus h plus 1 and x plus 1 on the top and the bottom. We're not going to do it because that's too much. All right, alternative form of the definition. Okay, it's going to come from the same thing, but the alternative form means slope at a specific point. Should have highlighted just the word specific. That's what I meant to say. The alternative form means slope at a certain particular point. What we had done before, like that 6x minus 2, that would tell me the slope at any point on G. I would just plug in whatever x is, and I would know the slope at that point. That's the more generic definition. The alternative form is a specific point, although it comes about the same way. Let's do our secant line, and we want to find f prime at a. We want to find the slope of the tangent line. Let's say this point is x. There's f of x. We're going to follow the same steps. Let's write the algebra slope first. So the algebra rate of change is f of x minus f of a over x minus a. And there's no h to change in this one to move my secant line to become a tangent line. So what could I move on this one? I can't move a because I want the slope at a. Let's move x. Let's move x toward a. So the limit as x approaches a, and then we'll just use the same algebra slope formula. And this is maybe weird, but this is the slope, not at any x, but at a. So that's the slope at x equals a. That's the important part. So the alternative form is nice, but it only gives you the slope at one particular point. And there it is boxed up, but that's the same thing we just did. Perfect. We got time to do one example, and that'll be enough. Find f prime at 2. So that 2 in there means we're doing at x equals 2. That means I need to do the alternative form. The alternative form is easier. It's just, it only tells you at 2. So if I needed the slope somewhere else, I'd have to redo the alternative form. So the generic form is nicer because it's like it tells you for everything, but it's longer. The alternative form is shorter, but I'm only going to learn the slope at 2. So let's see. Limit as x approaches 2, f of x minus f of 2 over x minus 2. So I need to find I have no f of x. I need to find f of 2 and then plug things in. F of 2 let's see. Oh, my poor Algebra 2 students. Order of operations, it's not a problem for you guys, I hope. 2 times 2 is 4, or 2 squared is 4? Which would you like to do first? Good. 2 squared is 4, times 2 is 8. Nobody was going to mess that up in here. So f of 2 is 13. Okay, everything else I know. Limit as x approaches 2. Here's f of x. That will go in for f of x. 2x squared plus 4x minus 3 minus f of 2, that's 13, all over x minus 2. Okay, so let's clean this up a little bit here. Limit x approaches 2, 2x squared plus 4x minus 16 over x minus 2. First go is always plug it in. What's going to happen if I plug in x equals 2? 0 in the bottom. So let's factor the top. I can definitely take out a 2. Running out of space here, but 2x squared plus 2x minus 8. That factor nicely. X plus 4 and x minus 2, which is nice because I was hoping the x minus 2 would go away. All right, so now this problem looks like what was on the last test, right? Factor, cancel, substitute again. 2 times 2 plus 4 is 12. So we're not going to do example 2, so we can write stuff down here. F prime of 2 is 12. What does 12 tell me about 2? Like, put it in words. Good. The slope at x equals 2 is 12. Again, we're trying to remember the concept of what we're doing, finding the slope at a point, but also there's also the process of doing all the algebra stuff.
So we can just take the derivative of the equation 1 implied in 2?
Okay, Mr. Shortcut. Yes, to check. Right? If it asks you to use the alternative form, I want you to do all this. But Will's question is, wait a minute, I know the shortcut. I mean, why not use the shortcut to check? So that would be 4x plus 4. Yep. And if I plug in 2, 8 plus 4 is 12. You can do that to check, Will. Yes. Right? In theory, we don't know this yet. But our pre-cals are so good that they got to this to help you out. So I still need you to do the ugly algebra. But yes, Will, you're right. Off to the side, you're like, wait a minute, I know how the better way to do this. Let me make sure, and yes, do that.
What was the shortcut for finding just like the regular derivative?
So you bring the power down front and reduce the power by 1. Does that sound familiar?
Yeah, okay. Yeah.
So 2 times 2 is 4, and then just the x, and then 4. And Mr. and Mrs. Shortcuts. That's what we're going to do tomorrow, is the shortcut. The shortcut method that you already